Imagine a world frozen solid, encased in ice from pole to pole. No life roams these frozen plains. Only glaciers move across them. This is not some distant planet starved of sunlight. According to a radical theory, this was Earth, 650 million years ago. No one knows what triggered this calamitous freeze. But if it happened once, could it happen again? Imagine the most profound ice age you can think of. Temperatures plummet to below zero, even at the equator. Before long, ice encloses our entire planet. Research suggests that this may have happened not once, but 3 times in our planet's past. Welcome to Snowball Earth.
Snowball Earth is certainly the most extreme climate change we can conceive the Earth having ever experienced.
What would happen if the world froze over today? Massive glaciers creep from the poles, crushing everything in their path.
First of all, the Canadians are going to have to dig much deeper holes when they go ice fishing. Next, the governors of Washington, Idaho, Montana, North Dakota, Minnesota, Michigan, and Maine will probably declare federal emergencies.
Cities grind to a halt. Power lines collapse and water supplies freeze. Cars won't start. Roads are cut off by ice. Buildings strain and crumble under deep drifts of snow. Everything is entombed. Our frail bodies struggle to survive.
I think human society would collapse if a snowball Earth happened again.
The oceans freeze over. Fish die and marine ecosystems collapse. Our food supply becomes exhausted. Any surviving humans are trapped in an icy hell.
We would have a mass die-off of humans simply because we could not grow enough food under these conditions.
Incredible though it may seem, the Earth may have frozen over completely. Scientists are finding clues in unexpected places. The story begins with a mystery. In the arid Flinders Ranges in southern Australia, layers of ancient rock hold unusual stones. These stones are foreign to the area. They are known as dropstones. The dropstones are embedded in an ancient sedimentary sea floor that formed around 650 million years ago. Tim Raub, a geologist at the Californian Institute of Technology, hunts for these dropstones at the Flinders Range.
This is an example of a dropstone, a piece of ancient rock that was dropped into the ancient mud on the sea bottom.
These dropstones are visibly different from the sedimentary bedrock around them. Something powerful must have carried them here. But what? Dan Schrag, professor of Earth and Planetary Sciences at Harvard University, believes the answer is glaciers.
We actually have ice cubes here that we've made with pieces of sand and gravel in them. So these ice cubes are like the glaciers that are taking rocks from the land, and then when we put them in the water, they'll actually melt and the sand and gravel will fall to the bottom, just like the dropstones on the ocean floor.
These dropstones are evidence that at some point, this area was covered in a thick layer of ice. But it's difficult to explain how ice could have covered the sun-baked mountains of southern Australia. Unless the continent itself was in a very different place. The continents haven't always been where they are now. They move very slowly across the Earth due to the movement of tectonic plates. 650 million years ago, around the time the Flinders dropstones landed here, the continents were positioned very differently. Since the dropstones formed under ice, perhaps Australia sat nearer to the poles where temperatures were lower. To locate the position of a continent in the distant past, scientists study the magnetic identity of rocks. Certain sedimentary rocks contain magnetic particles. When the rocks form, these iron particles line up with the Earth's magnetic field. Near the poles, they align at right angles to the sedimentary layers. And around the equator, they align parallel to the layers. Even if the rock moves, the distinctive configuration of these magnetic particles remains the same and provides a kind of geological fingerprint of the rock. Professor Joe Kirschvink at Caltech Pasadena is fascinated by magnetism.
Magnetism is magic. I've even named my eldest child after a magnet, so I enjoy magnetism.
Kirschvink and his team analyzed the 650 million year old rock surrounding the dropstones. The results were unexpected.
That part of Australia was within 5 degrees of the equator, and it just was the most weird place to expect a glacier.
But Kirschvink had to be sure that this ancient rock still held its original magnetic signature. If the rock heated up after it formed, its native magnetism would have changed. Back at Flinders Range, Kirschvink's team uncovered clearly striped sedimentary rock that provided proof.
Here, tens of thousands of layers of mud grew one at a time, upward and upward, in a glacial lake at the edge of a 635 million-year-old ice sheet.
When this rock formed, layers of sediment built up in distinctive horizontal lines. By comparing the direction of the layers of sediment with the direction of the lines of magnetism, Kirschvink could determine whether the rock's magnetic signature had changed.
We can explain the process of magnetism with a simple eraser. If the rocks formed on the equator and gained their magnetism very early, we would expect the magnetic direction to be parallel to the bedding very precisely like this. And then, since the rocks are soft, if they get squeezed or deformed geologically, you would expect them to rotate like this, and the magnetism would shift with the bedding. On the other hand, if the rock had been squeezed and deformed first, and then gained the line of magnetism like this, we would see them warped relative to the bedding today.
If the rock still had its original magnetic orientation, the lines of magnetism would follow the lines of sediment. But if its orientation had changed, the magnetism would cut through the sedimentary layers. Raub drills into the formation to retrieve solid cores of the rhythmic rocks. Back in the lab, the team analyzes samples of rock using a custom-built hypersensitive magnetometer. This magnetometer measures the orientation of the magnetic particles in the rock. It confirms that the particles were aligned with the rock layers. Kirschvink was astonished.
Quite frankly, when I saw the original study, I didn't believe it. And what in fact we see is that they're like this, and as the rock was warped, magnetism warped. That proves conclusively the magnetism formed before the rock was solidified.
This discovery seems to provide irrefutable evidence that the glacial rocks formed close to the equator. Paul Hoffman, professor of geology at Harvard University, was intrigued.
So if there were glaciers close to the equator, where the temperature was warmest, one has to assume that there was also ice in higher latitudes where the temperatures were colder.
650 million years ago, Australia sat near the equator. And yet evidence suggests that its arid rocks lay buried beneath ice. And if there was ice at the equator, there would have been ice all over the globe. These dropstones became the catalyst for a radical theory: Snowball Earth. This is a theory about the most extreme ice age imaginable. And if it happened before, it could happen again. Our world has been through many periods of extreme climate change. But some scientists have proposed that 650 million years ago, the Earth may have frozen over completely. This radical hypothesis raises one crucial question: how could it have happened? Kirschvink proposes that the giant freeze was triggered by the same mechanism that lies behind today's global warming, the greenhouse effect. Except 650 million years ago, it worked in reverse. Greenhouse gases in our atmosphere act like an insulating blanket, trapping the sun's energy to keep Earth's temperatures mild. When the snowball began, scientists suspect that levels of these vital gases fell dramatically.
The Earth's atmosphere might have been filled with methane and carbon dioxide, and the Earth became addicted to this high-level carbon dioxide and methane in order to keep its temperature. Then, if some unknown event crashed the carbon dioxide out of the atmosphere, Earth might have run away into a snowball Earth.
If enough carbon dioxide had been pulled out of the atmosphere, an anti-greenhouse effect would have plunged the Earth into a deep freeze. But this theory is only possible if there's a mechanism that could pull all the CO2 out of the air. In fact, carbon dioxide is removed all the time through a process called silicate weathering.
Weathering is a geological term for the decomposition of rocks under the influence of the weather. It's a process that converts solid rock into soil. Now, its importance for the climate is that weathering consumes carbon dioxide, which is a major greenhouse gas in the atmosphere.
Carbon dioxide reacts with water vapor in the atmosphere to form carbonic acid rain. This acidic rain weathers limestone on land and carries away the eroded sediment to the sea. Here it builds up, eventually forming limestone on the sea floor.
So the presence of the limestone is the evidence that weathering is occurring.
The more carbon dioxide gets locked away in limestone, the cooler the Earth becomes. But if this is happening all the time, something must have amplified the process for the whole world to have frozen over. Again, clues lie in the position of the continents. The movement of tectonic plates continually shifts the continents around the globe. Today, a lot of the continents are located in higher latitudes. If the Earth cools, the continents near the poles ice over. The ice prevents the rocks beneath from being weathered by carbonic acid rain. This means that the weathering cycle is kept in balance. With less carbon dioxide locked away in limestone rock and more in the atmosphere, the planet warms. Scientists have worked out that 650 million years ago, the continents were clustered around the equator, where it's warm and wet. Consequently, the global rate of weathering would have been higher.
During the Snowball Earth, we suspect that there were many more continents at the equator, and this would actually lead to a situation that would make the planet vulnerable to a global glaciation.
As the Earth cooled, ice formed at the poles, but because there were no continents in the higher latitudes, ice accumulated on sea rather than on land. There was nothing to regulate the weathering. The cooling continued unchecked, and the world got colder and colder. This runaway scenario is certainly plausible. But although extreme weathering could be behind an ice age, it doesn't explain how the Earth could have iced over completely. Geologist Galen Halverson from Adelaide University studies triggers of the snowball.
One of the hardest parts about understanding the snowball is really how it began. We think that it must have began like a normal glaciation.
Normally, living things help to regulate the Earth's climate by maintaining the delicate balance of carbon dioxide. Plants consume carbon dioxide. Animals produce it. These consumers and producers help to regulate the climate, ensuring the Earth is neither too hot nor too cold. If there's more carbon dioxide in the atmosphere, it gets warmer. This causes plants to grow faster, which in turn draws out more CO2 from the air.
So that is a feedback against it getting too warm. And in reverse, if it starts getting too cold, then the biosphere responds by not drawing down as much CO2, and that allows CO2 to go back up. So there's a sort of buffer in the form of life on Earth that prevents temperatures from getting too cold or from getting too hot.
But rewind 650 million years and witness a very different story. Life on land was in its early stages of evolution. Most living things were in the oceans. This half-formed biosphere could not prevent the Earth from swinging to wild extremes of temperature. Colonies of single-celled organisms called cyanobacteria were the first to photosynthesize. They pulled carbon dioxide from the surrounding water to precipitate calcium carbonate, and they used this to make dome-like structures of rock. Geologist Jim Gehling is an expert on these early life forms.
Temperatures were dropping at this time, 650 million years ago, for the very good reason that carbon dioxide, the principal greenhouse gas, was being taken out of the atmosphere and locked away on the seafloor.
This trapped carbon dioxide can still be seen today in stromatolite reefs.
This is actually solid carbon dioxide, and I can release that carbon dioxide after all those hundreds of millions of years when I put this weak acid on the rock. And there you see it erupt as the white bubbles of carbon dioxide spring out of the rock, go back into the atmosphere to take up their role all over again as greenhouse gases.
The more carbon dioxide the cyanobacteria locked away, the cooler Earth became. Our planet was hurtling towards a deep freeze that would last for millions of years. $650 million years ago, the Earth's temperature plummeted. Huge sheets of ice spread across the planet. Eventually, they engulfed most of the land and sea. This was no regular ice age. Ice ages are nothing out of the ordinary. We experience them every 100,000 years or so. They are mainly caused by small changes in the Earth's orbit, which alter its position relative to the Sun. When our planet receives less of the Sun's energy over a number of years, ice forms high in the northern hemisphere and advances down. At the height of the last ice age 21,000 years ago, these icy sheets reached down as far as New York. But the tropics stayed warm. Only about 30% of our planet froze. But 650 million years ago, some scientists believe the ice kept coming, until eventually, most of the globe was covered. What could have caused this runaway cooling? The answer must lie in how our planet keeps or loses the sun's energy. The Earth's surface is made up of land, open ocean, and ice. These all reflect sunlight to a different degree. The amount of light a surface reflects is known as its albedo. Deep dark ocean has a low albedo, since it absorbs a lot of sunlight. white snow and ice have a very high albedo, since they reflect more of the sun's energy back into space. Tim Raub demonstrates how dark and light colors heat up under the sun.
The temperature of a white car sitting in the sun is only 120 degrees. The temperature of a black car sitting in the sun is 144 degrees. The black car absorbed light, the white car reflected it.
White reflects more sunlight, keeping whatever it's covering cooler. The more ice that covers the Earth, the more of the sun's energy reflects back into space, and the colder the planet becomes. This cooling leads to more ice forming, which further increases the surface albedo. This is known as ice-albedo feedback. And something may have accelerated this cycle of cooling even more. New research suggests that when seawater freezes at very low temperatures, its composition changes, and it can become more reflective. At the University of Washington's Polar Science Center, Bonnie Light studies the relationship between ice and light. In the cold room, she freezes buckets of salt water at different temperatures. One of the buckets is exposed to Snowball Earth temperatures of -10 degrees. The surface of this ice becomes much whiter.
Okay, so this bucket contains seawater that was frozen in a cold room at 5 degrees above 0 Fahrenheit. And we consider this a good laboratory analog for modern day sea ice on planet Earth. And you can see that the surface of it is kind of gray colored, dull appearance. And this bucket also has salt water in it, although this salt water was frozen at about 10 degrees below 0 Fahrenheit. And we consider the ice in this bucket to be a good analog for sea ice on Snowball Earth because it's very cold.
At Snowball Earth temperatures, the composition of sea ice changes, turning its surface from gray to bright white.
And you can see that these crystals in this case have started to collect at the surface of this cold ice. And so I can kind of scratch away these crystals, and you can see that this is basically just a deposit on the surface of this cold ice.
At -10 degrees, salt molecules in the ice begin to form tiny crystals.
If you can isolate them under the microscope, they look like little gemstones. They're really quite beautiful.
These bright crystals have a dramatic effect on albedo. The white surface scatters more of the sun's energy and reflects it back to the atmosphere, causing temperatures to drop even further. In the 1960s, Soviet climate modeler Mikhail Budiko demonstrated how runaway ice albedo could cause a cooling Earth to freeze completely. Like many of his contemporaries, Budiko was worried about the effects of a nuclear winter. Nuclear explosions create clouds of smoke and dust, which block the sun's energy and lower the Earth's temperature. Budiko developed a mathematical model to work out the odds of a global ice age. He showed that if the Earth's climate cooled enough for ice to form in the lower latitudes, then the ice albedo would rise at a faster rate. And once the glaciers reached a certain latitude, the Earth would tip into a snowball-like state.
Somehow or the other, the ice line, the glaciers, reach some critical latitude, around 30 degrees. And once they hit that latitude, very, very rapidly, the Earth would have been entombed in ice.
Budiko's groundbreaking work showed how this snowballing effect could create a totally frozen planet within just a few decades.
Budiko's work was extremely important in demonstrating that it was possible that Earth might slip into a climate catastrophe which was covered completely with ice. It had not been recognized as a possibility before that.
If the Earth became entirely covered in ice, nearly all the heat it received from the sun would be reflected back into space. The planet would become locked in ice. So if runaway freezing trapped the Earth in ice, how did it ever escape? Some scientists suggest that 650 million years ago, our entire planet was locked in an extreme ice age. It was a unique event, the result of a set of improbable triggers. Or so they thought. Then, in 1997, evidence emerged that it could have happened more than once. It came from glacial deposits in South Africa that were over 2 billion years old. Paleomagnetic evidence suggests that these formed near to the equator. Geologist Paul Hoffman believes this could be proof that the Earth froze over completely at least twice in its history.
The best evidence for a snowball Earth 2.22 billion years ago is paleomagnetic evidence from South Africa. There are glacial tills there, boulder clays, that formed very close to the equator.
This discovery raised the possibility that the snowball wasn't a single event, but a recurring condition. Scientists raced to find the trigger for this earlier deep freeze. The cooling appeared to coincide with the Great Oxidation Event. Deep in the ocean, some of the oldest organisms on Earth evolved a mechanism called photosynthesis. The ability to convert carbon dioxide into oxygen using the sun's energy. As these photosynthesizing microbes thrived, they had a profound effect on the Earth's climate. 2 billion years ago, our sun was weaker. Our planet relied on greenhouse gases like carbon dioxide and methane to maintain its temperate climate. But photosynthesis uses up carbon dioxide. It also produces oxygen, which destroys methane. The result, a double whammy. Levels of both these vital greenhouse gases plummeted.
You have a precarious situation. You have a planet that's greenhouse needs methane, and you suddenly evolve a bug that destroys the methane.
Maybe the first bacteria that photosynthesized crashed the carbon dioxide and methane from the atmosphere and triggered the first snowball Earth.
As oxygen production soared, methane levels tumbled. With the loss of that greenhouse gas, the Earth spiraled into a deep freeze.
It's kind of a frightening conclusion that a single-celled mutant bug destroyed an entire planetary ecosystem. Destroyed it. Turned it into a snowball for maybe 35 to 100 million years.
Some scientists now think that our planet has been encased in ice on at least 3 separate occasions, and each time under different circumstances. But these snowball Earth scenarios present a huge problem. If our planet was trapped in ice, how did it ever escape? Something must have caused a global meltdown. Evidence of the thaw is right here. On top of the dropstones sit layers of a peculiar reddish-gray rock. These layers stretch for miles in the Flinders Range, Death Valley, and almost everywhere where the glacial rocks appear. These are carbonate rocks, which form in warm, shallow seas. But here, they appear right on top of the glacial deposits.
So here's a sample that actually shows the end of the snowball event. So that's an ice-rafted stone dropped out of an iceberg. And these are little grains that also fell out of an iceberg. And immediately on top of that, without any break in sedimentation, is cap carbonate that's precipitating directly out of the ocean and accumulating on the seafloor. And exactly the same relationship is seen all over the world.
Their presence is evidence of a sudden and drastic temperature increase. Only one thing could have triggered this: a huge injection of greenhouse gases such as carbon dioxide. In order to melt Snowball Earth, concentrations of carbon dioxide had to be around 350 times higher than they are today. But if the whole planet was encased in a thick layer of ice, where did the carbon dioxide come from? Caltech professor Joe Kirschvink had a revelation.
I woke up in the middle of the night and said, that's gotta be it. It just dawned on me that these subaerial volcanoes, like in the Aleutians and the Yellowstone, these volcanoes sit and they spew CO2 into the air.
Even beneath the ice, volcanoes would have continued to release immense volumes of carbon dioxide. With the rest of the planet still ice-locked, there would have been no mechanism to remove it from the atmosphere. Over millions of years, levels of this greenhouse gas would have built up, eventually producing enough warming to offset the ice-albedo. The ice melted, sending global temperatures spiraling upwards. As this melted ice water evaporated, it swelled the atmosphere with moisture, creating torrential rainfall. Carbon dioxide in the atmosphere acidified the rain. Acidic downpours rapidly eroded limestone, washing sediment down into the oceans. Here, layers of carbonate sediment accumulated on the sea floor to become carbonate rock. Dan Schrag demonstrates what could have happened.
Instead of carbonic acid from carbon dioxide, we're going to use a little stronger acid to make it go a little faster. This is nitric acid, and when we add it to the limestone, it will dissolve away the limestone and ultimately create a very clear solution. So you can see it bubbling away. And when this is added to the ocean, it reacts and creates the cap carbonates that blanket the top of the glacial deposits.
But still, not everybody is convinced that the planet was ever entirely covered in ice. Some scientists argue that the chances of life surviving a full-on snowball are virtually nil. Above the ice, the freezing conditions were too hostile, while below it, life was cut off from sunlight. Yet there is evidence that photosynthesizing organisms did survive the freeze. Single-celled cyanobacteria existed right the way through. Cyanobacteria can survive extremes of temperatures many degrees above and below zero. But if the oceans froze over, a thick layer of ice would have sealed them away from the sunlight. With their energy source blocked, they would have died out.
If you'd been diving on a tropical reef before Snowball, this is what you would have seen. Slime world, mounds of slime on the sea floor. And if you touch them, you'd find out that they're actually rock. A surface covered with slimy material, which is actually cyanobacteria, the earliest, the most primitive form of life that's been around for 3 billion years up until this point, and is still around today.
Critics argue that nothing could have survived the ferocious conditions of a total global freeze. They maintain Snowball Earth was nothing more than a severe ice age with extensive glaciers and a belt of open water around the equator. Philip Allen, a geologist at Imperial College London, believes that the evidence for a frozen planet is flawed.
I am not in agreement with the Snowball Earth hypothesis. The major hole in the theory, as far as I'm concerned, is that the sedimentary rocks deposited during the glacial periods do not support the idea of a long-term global freeze.
Philip Allen's counter-evidence includes the ripple-like patterns in rocks formed 650 million years ago.
When you look at those sedimentary rocks, it indicates open water. The wind was able to blow over the water surface and form ripples, wave ripples on the seabed. So they are really conclusive proof of an open water surface rather than an ice-covered one.
Waves in an open sea left imprints in the sediment of the sea floor. When the water disappeared and the sediment turned into rock, the ripples remained. Allen and others propose an alternative to the Snowball Earth. It's known as the slush ball. In their version of events, the Earth never froze completely. Some patches of open land and sea remained. But proponents of the snowball theory don't suggest that the frozen planet was without any open water. Schrag believes that life could have survived in ice holes around sources of geothermal energy.
Even in a completely ice-covered planet, there's still plenty of places where there are hot springs, geothermal heat from volcanoes, probably thousands and thousands of such little holes. And in many of those little holes, you could sustain life throughout the Snowball Earth period.
The reality is, we may never know if the world was ever completely frozen over.
Sometimes people think of the Snowball Earth like a cartoon, an oversimplified planet. But the real world is much more complicated than that.
Whether slush ball or snowball, everyone agrees there was a profound global freeze. And when our world emerged, 635 million years ago, something unexpected appeared. Life. Far more complex than anything that had gone before. After the big freeze, life on Earth exploded. Our planet, 650 million years ago. Temperatures plummeted, turning our planet into a hostile place. Yet somehow, life survived. And as soon as the frozen Earth began to thaw, it blossomed. And there was an unprecedented explosion of life on Earth. Before the deep freeze, life was primitive. Single-celled organisms and algae were mostly confined to the oceans. Shortly after it ended, the first multicellular animals appeared. The big question is, did the global cooling trigger this great leap in evolution?
Well, the best evidence is the coincidence in timing. The fact that the first fossils of multicellular animals occur less than 3 million years after the last snowball termination.
Shu-Hai Xiao is a geologist at Virginia Tech. He unearthed some of the oldest multicellular animal fossils in the world in a mine in southern China.
The fossils are really small. They're about half millimeter in diameter, so you can barely see them with naked eyes.
Under a microscope, he discovers that the fossils are very primitive animal embryos. Some fossils show clusters of 2, 4, 8, and more cells.
It was really exciting when we found those. Those are some of the earliest animal fossils, and they have found in rocks that were deposited almost immediately after the Snowball Earth ended.
Fossils of these animal embryos date back to just 3 million years after the global freeze ended. That might seem a long time in human terms, but geologically, it's the blink of an eye. Over the next 80 million years, animal life exploded. In the Flinders Ranges in southern Australia, geologists have found some of the oldest fossil evidence of complex multicellular life. These creatures bear little resemblance to life today, but they offer clues to the genesis of early life. 650 million years ago, this area was beneath a shallow sea. Bizarre, soft-bodied organisms similar to jellyfish or flatworms lived on the sea floor. Some of the organisms got trapped in fine silt of tidal flows where they fossilized. Jim Gehling has been investigating these early animals.
Probably our ancestors lie in these rocks. This thing here, Dickinsonia, can best be described as some kind of a pancake or mat-like worm creature. It doesn't have a proper head, it has what appears to be a gut, very fine segments.
But this doesn't explain how the severe planetary freeze could have triggered a leap in evolution. What we do know is that there is a striking coincidence between the rise of oxygen and the end of the snowball. Oxygen levels rise following these global ice ages because of a chemical reaction between ice and sunlight. 650 million years ago, there was no ozone to stop the sun's ultraviolet light hitting the Earth's icy surface. This UV light reacted with water vapor to form hydrogen peroxide. The hydrogen peroxide remained in the ice for millions of years. But when the ice melted, the hydrogen escaped, and the peroxide converted into water and oxygen. Oxygen reached the same level as we have today. At roughly the same time, the first complex animals appeared. More oxygen enabled life to become multicellular. A single cell can take up gases and oxygen from water. Oxygen fuses across the cell membrane into the cell. However, when several cells link together, it's harder for oxygen to diffuse from one cell to the next. The pressure of oxygen needs to be higher.
You need to have a high enough pressure of oxygen to have a circulatory system bring the oxygen all around the body. After the last Snowball Earth, oxygen seems finally to have been high enough to support hundreds, thousands, millions of small early animals on the seafloor.
Oxygen turned out to be the linchpin of evolution. The ability to use oxygen enabled life to become dramatically more diverse.
Oxygen gives us 20 times more energy, or more than 20 times more energy, than any other thing that we can breathe, or that life can breathe. You can have bigger animals, you can have more active organisms, you can have plants that grow and transport liquids from roots to the leaves, and you can have birds energetic enough to fly. Without oxygen, we would all be slime.
A frozen Earth may have given early life a push forward. But if the world were to freeze over again, we'd struggle to survive. We know it's happened several times before. The question is, could it happen again? One factor in our favor is the sun. Over the last 4.8 billion years, it has been getting more and more active as nuclear fusion generates more and more heat. The sun today is about 6% warmer than 650 million years ago. So in the short term, another deep freeze is unlikely.
The sun is warmer today. That probably helps us out. But until scientists really understand what causes snowball Earths, I don't think any of us know whether we're in danger or not of a recurrence.
But there is one possibility that could result in another global freeze: a shift in the position of the continents. We know their arrangement influences the climate. If the majority of the continents were clustered on or near the equator, the Earth would be more likely to turn into a snowball. Cooling temperatures would cause ice to form in the open ocean of the poles, while weathering would continue on the continents. With more and more carbon locked away, temperatures would plummet.
If all the continents were near the equator, then the Earth could get colder and colder, and sea ice could form and get to lower and lower latitudes, closer and closer to the equator.
Today, our world seems safe. Most of the continents are near the poles. But plate movement never stops. At some point, millions of years in the future, the continents may group around the equator once again.
I think it's possible someday, if the continents were in a very different position, maybe hundreds of millions of years from now, that we could indeed have another snowball Earth.
It's unlikely that mankind will be around to witness another snowball Earth. But the Earth will still be here. And just like it has in the past, our planet will survive and enter a new phase in its extraordinary history.